Alright, one of my favorite subjects to talk about. I've actually been wanting to do this video, so I'm really glad it was asked for, because it gives me a reason to do it. Because self-motivation is lacking here, apparently. Alright, so we're going to talk about roots and factoring the prime factorization is really what this is called. And I just want to point out that this is your radical. And it has, just like when we say x, there's an understood 1 here. When you have a radical with no numerical markings, then it is just understood to be to the second, or it's the opposite of a squared. So the square root of a number squared cancels, just like adding and subtracting 1, and then taking a number, adding 1 and subtracting 1 also cancels the number. This does the exact same thing. I always talk about operators and making sure we understand their opposites. Well, taking the square root of something is the opposite of squaring something. And then this is just another way to write both of these things. And this is your power that it's being raised to, and this is the root that you're taking. So this is the same as raising x to the first power while taking the square root. As you see, since this is an understood 2 out here, these do not naturally cancel, and therefore we will get a different x value once we take its root. So let's do that. Let's talk about factoring out some numbers to their prime factored form. I'm going to start with 34. So I'm going to know that this is an understood 2, and that's going to be very important once we get this factored out. So let's go ahead and start factoring. Again, if you watched the first video, that's fine. If you haven't, always start with the lowest prime number that the number can be divided by, and move up from there until you cannot divide anymore, and then you have your prime factors. So 2 is prime, and I know that 2 times 17 gives me 34. You don't have to go searching. I know 17 is prime, so 34 is already factored. The square root of 34 is in its factored form. So we're not going to go any further on that one. But we are going to move on to, let's do, how about 44? So if I want to get the prime factored form of 44, we're going to divide u. So we know that 2 times 22 is 44. Now I look at 22 and I say, well, that's still divisible by 2. And 2 times 11 is 22. Now remember when I said how important it was to remember that this is an understood 2? When you factor under a radical, you have to take everything out in pairs to make it whole. What does that mean? Let me show you. So I have 2 2's. I can go ahead and circle those because those are my pairs or my 2's. So I know that I can now take this out of the radical as a 2. And then I only have 1 11, so I leave that under. Now I'm left with the square root of 11 times 2. 2 is prime, 11 is prime. Now I'm going to do another example in a few minutes here where the number on the outside of the radical is a composite number and it's not prime, and that's perfectly fine. We want to leave the prime number under the radical. I hope that makes sense. So real quick, we're going to verify that the square root of 44 is indeed equivalent to 2 times the square root of 11. Real quick, we're going to take the square root of 11, which is 3.31 approximately, and we're going to multiply it by 2 because we have the square root of 11 times 2. This is an understood multiplication, and when we do that, the calculator is spitting back 6.63. Let's just leave it at that for now. This is not exact, this is just showing you how to do it. So now to check the answer, we're going to take the square root of 44, which is 6.63. So those are equivalent, so we've done this correctly. Now let's move on to a number where we're going to have a composite number outside of the radical and a prime number inside. Prime factorization literally means what prime number will we be left with under the radical. So we're going to throw one together off the top of my head here. We're going to have 567 and see if that shows us a prime factorization with a composite number outside the radical. It's like I said before, prime factorization only is concerned with having a prime number underneath the radical. So we have 567, clearly not divisible by 2 because it's not an even number. Is it divisible by 3? Yes. And the easiest way to know that is that the sum of the components of 567 is 18. 18 is divisible by 3, or the sum of the components of 18 is 9. That's divisible by 3. Therefore, this is divisible by 3. And that will give us 189. 1 plus 8 plus 9 is 18. That's also divisible by 3, which would give us 63. 63 is divisible by 3, which gives us 21, 3, and 7. All right, so now, again, this is another key point. This is a really good number. I'm glad this is the one I kind of picked here out of thin air. This shows us that, remember, it's the 2 that we're really concerned with. It's an understood 2. This is what we need to do. We need to pick them in pairs. So we have a pair of 3s here, and we have a pair of 3s here, and then the 7s all alone. So what we actually end up with, oh, that is not the right color. Let me swap over to this one. All right, we have the 2 3s here come out of the radical because it is a 2 here. You need pairs, so it comes outside of the radical. Here's another pair of 3s. They come outside of the radical. You multiply these together, and then you're left with 7 under the radical. 7's a prime number, so this is a prime factor. And then we are going to do, excuse me, we have 9, because these 2 multiply to 9, square root of 7. So now here's the other trick. Remember I said earlier how important it is to know the opposite of an operation: plus, minus, multiplication, division. They're all opposites. Squaring and square root are opposites of each other. So if I want to cross this barrier, I had to pull out pairs here. But if I want to put a number back in, when we're talking about this 9, to cross this barrier, we also have to square the number to make it fit inside the radical. So what we really have here, if we want to check our work, is 9 squared times 7. 81 times 7, we're going to use a calculator on that one, is 567. That's a quick way to check it. So now we do know that we were correct in saying that 9 times the square root of 7 is the prime factorization of this number. So now we're going to do one more special case, and that is when we have a perfect square under the radical. And I think if we kind of think about it for a minute, what's going to end up under the radical? Well, nothing, because it's a perfect square. So let's pick 225. Clearly divisible by 5, and that would be 5 times 45, which is 5 times 9, which is 3 times 3. So we're looking for the square root, understood 2. We conveniently only have 2 5s and 2 3s. So we know we can bring these over as 5 times 3, which gives us 15. 15 times 15, or 15 squared, is 225. This checks out. So we now know that the square root of 225 is equal to 15. That is prime factorization, second root. The next video is just going to be in general, third, fourth, nth root. What do we do? How do we know how to do it? It's really simple. It goes right in line with this video. Thank you.